Now that we've configured the mapping of our inheritance hierarchy, let's start interacting with it and see how we can add and fetch instances of our new entity types on the database. We're now inside Visual Studio and we're looking at the program class of our console application. So the first several lines of code that we see here add a number of entries to the items table. First we add a canned food item, which is an instance of an energy drink. For this we specify a price and a weight, and we also specify that the can is made of tin, the drink expires a year from now, and it was produced a year ago. Then we add another canned food item, this time a can of tomato soup. This item also has a price and a weight, the can is made from steel and it expires in 3 years and was produced a year ago. Similarly, we add a dried food item called dried tomato soup, a clothes item which is a pair of hiking shoes made from leather, a magazine item called Climbers Quarterly, which surprisingly enough is published once every quarter, and finally an instance of the item-based entity called Knotting Rope. After adding all these items to the items collection, we call the save changes method on the database context and then proceed to fetch these items from the database. Before we start fetching the entities, we first call the clear method on the change tracker of our database context. This is definitely not something that we do during production, but we do it for the sake of the demo, because otherwise the entities that we would be fetching would be coming from our context change tracker and not freshly from the database. And after having done so, we first fetch all the items from the items table using this bit of code here. And after this, we fetch all magazine entries from the items table in two ways. First, we fetch them by using the ofType method on the items collection on the database context, passing in the magazine item type as the generic input parameter. And secondly, we do so by directly querying the magazine items collection on the database context. As we shall soon see, both approaches yield the same result and leads to the exact same SQL being executed on the database. For most cases, using the dedicated collection will probably be more convenient, but depending on our needs, it might be relevant to know that we can fetch specific entity types in this way. After having done so, we proceed to fetch some of the other item types that we've just created, beginning with the canned food items, followed by the dried food items, and then finally the clothes items. As we can see, we use the same approach for fetching these types of items, and the same approach can be used for any of the items that are derived from the item base entity. Notice that we don't have a collection for specifically fetching the uncategorized items. This is because fetching from the items collection on the database context doesn't just fetch the base entity, but rather it fetches all types of entities in the items table. If we want to be able to specifically fetch only the item base entity, we have to go over to the item class and specifically add the discriminator as a property, like we see here. And then we have to head over to the configuration of the item entity in the database context and change how we set up the discriminator to start using the new property. Making these changes only change how ifCore maps the discriminator to our item type, so there's no need for us to create a new migration. ifCore will simply switch from creating a shadow property for us to using the string property that we've just created. And if we now head back to the console application, we're now able to query for the uncategorized item entities. But we do so slightly differently than we did for the other item types by using the where method to specify that we are only interested in items whose item type discriminator is set to uncategorized item. And now let's run the code and see all of this in action. We'll start by quickly moving past the first several lines of code where we add the new entities to the database and clear the change tracker. After having done so, let's head over to the Server Explorer. As we can see, several new entries have been added. Here we have the energy drink and the canned tomato soup. And as we can see, the canning material column is filled out for these two entries with tin and steel respectively. Likewise, the expiry date and production date columns are filled out with the relevant dates. But as we can see here, they have a null value in both their fabric and publication frequency columns, since those columns only pertain to the clothes item and magazine items respectively. If we instead look at the hiking shoes below, we can see that it has no canning material specified, but rather the fabric column tells us that these shoes are made from leather, and so forth for the other items which have been added. And finally, of course, we have the item type column, which tells us and ifCore if we're dealing with an uncategorized item, a canned or dried food item, a clothes item, or a magazine item. And if we now head back to the console application and move the debugger past this bit of code here, we fetch all items from the items table. And as we can see here in the watch view, we get 8 items back of the various types in our inheritance hierarchy. We can also see that it includes the items that we just added, as well as our 2 existing items, which we see here. And if we look here in the output window, we can see that ifCore executed a select statement on our database, which simply fetched all rows from the items table. And if we move one step further, past this bit of code here, we fetch all magazine items from the items table using the typeOf method. As we can see here in the watch view, we get one magazine item back, and if we expand that item, we can see that it's the climbers quarterly. And if we once again look in the output window, we can see that ifcore has executed the select statement once again, this time adding a where clause stating that we only want magazine items, or rather items whose item type discriminator is equal to magazine item. If we now take one more step with the debugger, past this bit of code here, where we use the magazine items collection to fetch the magazine items, we can see here in the output window that this executes the exact same query, and if we look in the watch view, we can see that we once again fetch the climbers quarterly magazine. If we now proceed with the debugger to fetch the canned food items, we can see that this executes a query in the items table for entries whose item type is equal to canned food item. And if we move past the next bit of code here, which fetches dried food items, we can see here in the output window that a query has been executed for entries whose item type discriminator is equal to dried food item. And of course, if we move past the next bit of code here, which fetches clothes items, we get a query for entries whose item type discriminator is equal to clothes item. And if we now move past this last bit of code, where we fetch the uncategorized items using the where clause, we can see that we've explicitly created a query like the ones that we saw before, where we query for entries that have an item type of uncategorized item. Also note that because we added the include statement to include item orders, we also get a left join to the item order table. We did this to show that even though we are now using the items table to map our inheritance hierarchy, we can still fetch our item orders from it. If we open up the watch view, we can see that we get 3 items back, which corresponds to the knotting rope that we just added and the 2 items that already were there. If we expand the last one, we can see that it's the knotting rope that we just added. If we instead expand the first one, we can see that it's the item with ID 1 that we've worked with so many times now. And if we expand its item orders collection, we can see that it contains 3 items just like we would expect. Even though the items table now also serves the purpose of mapping our type hierarchy, we can still fetch our item orders using our navigation properties. In the demos that we just saw, we mapped our model to the database using the table per hierarchy mapping strategy. We then saw in the demo how we could add data to our new items model, and we then fetched this data back from the database. And in the process, we looked at how we can fetch all items from the items table, but also how we can specifically query for entries that are derived from the item base class, such as for example the magazine item entity type. And as we were querying the different items collection on our data model, we saw how ifcore fetched the individual item types by simply generating queries on the database, which filtered on the item type discriminator of the entries in our items table. In this module, we looked at mapping inheritance to our database using the table per hierarchy strategy. Using that strategy created a schema on our database where each entity in our inheritance hierarchy was mapped to a single table. I hope you enjoyed this module. In the next one, we'll look at using table per type and table per concrete type to map our inheritance hierarchy to the database. Hi, and welcome to the Mapping Real-World classes in ifcore 6 course. My name is Torben Jensen, and in this module we'll explore how to map .NET type hierarchies to a database using the table per type and the table per concrete type mapping strategies with ifcore. In the previous module we looked at mapping our .NET type hierarchy to the database using the table per hierarchy mapping strategy. In this module we'll look at doing so using the table per type strategy, which as mentioned in the previous module was introduced with ifcore version 5, and table per concrete type, which was introduced with ifcore version 7. Now that we've looked at the table per hierarchy strategy, let's turn our attentions to the table per type strategy. This mapping strategy was introduced to us in .NET Core version 5, and it differs quite a bit from the table per hierarchy strategy in that it maps all types to individuals as opposed to every type being mapped to a single table like it was when we used the table per hierarchy strategy. This means that individual tables exist for the base entity type as well as all of its derived types that are part of our data model. These tables are used to store the properties that are specific to each entity type. This also means that properties that are defined explicitly on the base type, therefore are shared with all its derived types, are stored in a table that is mapped to that type. And similarly, tables which are mapped to the derived types contain columns for properties that are specified on these types. These tables also contain a foreign key that joins the derived table with the base table. This creates a database schema where table joins will frequently be needed for querying data. Such frequent join activity will often lead to the table per type strategy having rather poor performance when compared to the table per hierarchy strategy. And after the introduction of the table per concrete type strategy, which we shall soon talk about, and which has many of the advantages of the table per type strategy without its poor performance, it is no longer recommended for us to use this strategy. Nonetheless, we may run into having to deal with this strategy, so let's take a look at how our model looks in context of it and also see it in action in the upcoming demo. So here we once again see our item model, which we must now map to the database using the table per type strategy. Unlike the table per hierarchy strategy, table per type does not map everything to a single table, but rather creates a table for each of the types in our inheritance hierarchy. What we see here is once again a slightly modified version of the actual model on the database. And as we can see, our database schema now contains 5 tables, one for each type. So here we have the items table, which contains entries for all the items regardless of their type. This also includes items which are directly of the item base type, and as we can see, this table contains columns for properties that are explicitly defined on the item type and are shared across all its derived types. In addition to the description, unit price and unit weight, it of course also has an ID column. That ID is used to connect the data in the items table with the additional type-specific data. So if, for example, we take the hiking shoes here with the ID 1028, we know that they are a clothes item. And as we've already discussed, we know that the clothes item table will have an entry with the same ID, which also serves as a foreign key relationship to the items table. So here we have the clothes items table, which contains a single entry with the ID 1028 and a fabric column specifying that these shoes are made from leather. When we want to query the database for clothes items, IF-Core will create a SQL statement that fetches data from the items table, which it then inner joins with the clothes items table, thereby returning only items which are also present in that table. The same would be the case, for example, for the Climbers Quarterly magazine, which we must look up in the magazine items table, which we see here. As we can see, that table has an entry with the ID 1031, which matches our entry in the items table, and we can create an inner join based on this. And once again, of course, the nodding rope is the odd one out, since it's an uncategorized item which is only defined in the items table.